This is Mr. Schwenke from Tyburn Academy. What we're going to do today is look at a concept in physics that is frequently misunderstood, or at least one that poses some challenges for students. That subject is circuits. An electric circuit is how we use electricity. We connect electricity. In this example here we have a plug connected to 3 light bulbs, and they're all in a row and they all light up when we turn it on. And that's handy if it's holiday lights or a set of lights to illuminate a building or whatever. But sometimes we don't want all 3 lights on. Sometimes we want to have independent control so that this light can be turned on and this one can be left off and this one can be turned on. This circuit has batteries powering it. So we have to consider 2 concepts called series circuits and parallel circuits. Series circuits are like a series on TV. You watch one show first, watch the next show a week later or next day or next month, whatever, and the third one can be last. And you don't do both of them at once. Parallel, these lines here connecting the bulbs are roughly in parallel, so that's where that name comes from. And since each of these bulbs is connected independently to the batteries, or it could be the plug if in your house, we can turn each of these things on or off independently of each other, and having one on or off will not affect the amount of electrical energy that the other one gets. So let's look at how to do these. We have a reference for our site, http Tyburn Science, that's all one word, the capitals don't really matter in a web address, tyburnscience.education, it's not just edu, and /physics and another slash. And that'll take you to our weekly sites that we do for, and have done for many weeks and years actually. Okay, let's draw a circuit using what we call schematic diagrams, and adjust this light a little bit. Our circuit is going to have resistors in it, so let's draw some resistors. We use a little symbol like this. Looks like an obstacle course. Up and down, up and down, up and down, up and down. And in fact, it is an obstacle course for the electrical energy running through it. We have to put some numbers on these to say how big or small they are. Let's call this guy 30 ohms. That little omega symbol, capital omega, is pronounced ohm, O-H-M in physics. Let's make this one be 50 ohms. Ohm is a unit that honors a German scientist named Georg Ohm in the 1800s. He was a high school teacher, actually. And he did experimental work to figure out how resistance worked and how combinations of resistances work. So we honor him with naming the unit of resistance after him. Let's come down now and put a battery in here. A battery has a symbol of little plates like this, little pieces of metal. And in fact, a battery in your car, if you could open those little caps on the battery top and look at it, you would see metal plates, copper and lead or zinc. And let's say this battery is 20 volts. We're just making up numbers here. We can put one more component in this circuit. We can put an ammeter. An ammeter is named after a French scientist named Ampere, who did studies with the flow of electrical energy called current, just like a river flow is called current, and is literally the number of electrons that flow through the wire. So now we have a circuit, because we can start here at the negative side of the battery. The current will flow through the ammeter, around through the 50 ohm resistor, through the 30 ohm resistor, and back. Now, obviously this circuit makes no sense. Why would we want to just have electrical energy flow through something that gets a little bit warm when energy flows through it, which is what resistors do? We can realize that these resistors would be something like a cell phone charger or a light or a television or whatever you have. These are the things that we use the electricity to power. And so we have to have circuits to get the energy to them. And the electricity has to make a complete trip. It can't just flow one direction and stop. It's got to get back to the source where the chemical energy in the battery will give it another boost, and around it goes again. Okay, let's do some simple analysis of this circuit. In order to see what this little guy, this ammeter, shows, we have to calculate what we call the equivalent resistance, which would be how could I replace these two resistors with just one to make it easier to understand. And R equivalent, we call it, for a series circuit is just the sum of them, R1 plus R2. And we can do this one in our head, 80 ohms. So this circuit could be replaced with one resistor of 80 ohms, and that's going to be R. V, the voltage, is 20 volts, and I, which is the current, now that makes little sense as well. I is the current. How come we have the meter that measures it be A for amps? Don't have a good answer for you. Physics has a few mysteries yet. But I is current, and we're looking for that. Another relationship in physics is V equals IR, and that's called Ohm's law. And voltage is equal to current times resistance, and often we turn those around. If we divide both sides of this guy by R, we'll get V over R is equal to I. We can do that. V is 20 volts. R is, the overall R is 80. So 20 over 80 looks like what? 1/4 or 0.25. So our current is 0.25 amps. And that's what this meter would show then. Last couple things we can do on this simple circuit is say if we connected up a voltmeter that measures voltage, not current. Voltmeter, maybe you've seen an electrician use one in the house looking for a lab, looking for what is a voltage, and it doesn't work the same way. Only a tiny bit of the energy has to flow through the voltmeter and back over here. It's like a tire pressure gauge. You don't have to let all the air of your tire out in order to see the pressure. You just unscrew the cap and put that little pressure sensor on there, and it senses the pressure. It's pretty much what a voltmeter does. So it's sensing the difference in electrical energy or voltage on either side of this resistor, because that energy is getting used up to do whatever this guy does. Maybe it's charging your cell phone or making the light go on over by the sink. But there'll be a difference in voltage in here, and we can see what that'll be. We can do V equals IR, Ohm's law again, and we'll do it with the things that we know. We know the current in this circuit is 0.25 amps, 0.25 amps, and that resistor is 50. So 0.25 times 50, I think, is going to give me 12.5, and that's the voltage that thing would show. The rest of the voltage will be used up by this. And that's pretty much what we do. We might sometimes have to do power calculations. Power is like watts. If you're sent to purchase a light bulb for somebody, you might ask them, what size do you want? 50 watt, 20 watts, you know. So power is watts, named after James Watt. And we have two formulas for that. Power is equal to current times voltage, and power equals I squared R. I is current. And we could figure out these for this little thing. Let's do the I times V for the one we've been working on. I is equal to what we figured out, 0.25 amps. And V is equal to 20. So 0.25 times 20 is 5, and that would be 5 watts. Okay, notice that in physics we always put the units. Everything has a unit so we can keep these guys straight. And next time we'll look at a parallel circuit, a little more complicated. If you have any questions, you can look at our website. It's tyburnscience.education, and then choose physics. Thank you.